Okay, welcome everybody. So far we've been talking about how we can apply matrix transformations to define linear transformations in R2, and in particular, to apply these transformations to an image on a computer screen, which would be R2, a flat screen. So the three transformations that we've looked at so far were a scaling transformation by a factor of 3. And recall that transformation is given by matrix S, which has its first column 3, 0, and its second column of 0, 3. And if we took one of the vertices of that triangle that we were looking at in the previous slides, then that first vertex at 1, 1 under this scaling map got mapped to 3, 3. And now we're going to compose this map with the two others. So let's say we first scale this triangle by a factor of 3. And then after applying that map, we next vertically shear that triangle by a factor of 2 in the vertical direction. So that means we're going to apply this matrix V, which was the first column 1, 0, and the second column 0, 2, to now, since we're composing maps, to the output of the previous transformation. So this 3, 3, just recall, that came from applying the scaling matrix S to this vector at 1, 1. And now we tack on to that vector V, and out comes 3, 6. So this column vector 3, 6, this is the result of first applying S, then applying V to the vector 1, 1. And then the third transformation that we looked at that I want to add on last was we did a counterclockwise rotation in R2 by 270 degrees, which was 3 pi over 2 radians. And that rotation matrix, we plug in 3 pi over 2 in place of theta, and then applying this rotation matrix R to the result that we got after applying the previous two maps. That puts us ultimately, this vertex at 1, 1 gets first mapped to 3, 3, then 3, 6, and then after this rotation, it finally winds up at its final point at 6, minus 3. And so this rotation matrix R we can think of as being applied to the vector which we got by first applying the scaling, then applying the vertical shearing, and then finally applying the rotation. So applying these three transformations in this order means we took 1, 1, we first multiplied on the left by matrix S, then we multiplied that on the left by matrix V, then we multiplied that on the left by matrix R. And by the associative property of matrix multiplication, we see that under the image of these composition of these three transformations, we could apply them in this sequence of order, or we could multiply the matrices in any other order that we like. So for example, I could first multiply S times V, V multiplying S on the left, and then we can multiply that by R. So we can find out what this matrix is by multiplying these three matrices together and then applying that single matrix to X, so that we can apply all three of these transformations by multiplying on the left by a single matrix that we get as a result of multiplying each of the three transformation matrices. Okay, so now let's see what happens if I apply these three transformations, the scaling by a factor of 3, vertical shearing by a factor of 2, counterclockwise rotation by 3 pi over 2 radians. If I apply them 1 by 1 by 1, and let's compare that to what happens if instead I were to take the product of those three transformation matrices first and then apply this map by multiplying X by the product of those three matrices. So in other words, doing them all at once. So going 1 by 1 by 1, for example, the vertex at 1, 1, we saw S, the scaling, first maps it to 3, 3, the vertical shearing then maps it to 3, 6, and then the rotation maps it to 6, 3. So let's plot each of those one by one. And so what would happen is this point at 1, 1 first gets scaled 3 times as far to 3, 3, then gets vertically sheared up to the point at 3, 6, and then gets rotated 270 degrees down here to the point at 6, minus 3. And we can apply each of those transformations to the other 2 vertices, and let's see what happens in each stage of this transformation. And so after applying the scaling, right, we get this scaled triangle over here that's going to be 3 times as large as the one that we started with over here. Okay, then we apply this vertical shearing. So each of these points in the red triangle that just got scaled, now we're not doing anything in the x1 direction, but we're just going to stretch this vertically. So we get these 3 new vertices, and now we get a scaled and then sheared triangle. And then the very last thing we're going to do is rotate this around counterclockwise 270 degrees. And so, for example, this point at 3, 6, it gets moved down to over here, at 6, minus 3. This vertex gets rotated 270 degrees over here, and then this top vertex gets rotated around 270 degrees over here. So we take this blue triangle, the red triangle is what we get when we do the scaling, then we vertically shear it to get this black triangle, and then finally we go ahead and apply the rotation by 270 degrees counterclockwise, and we get the green triangle. So now let's see what would happen if instead of applying them one by one, we just take the product of r times v times s and then apply that matrix to each vector x in our triangle. So in this case, the product of these 3 matrices, and again, it doesn't matter which I multiply first. So I can multiply the rotation times the vertical shearing, and then multiply that result times the scaling. And you'll see that after multiplying these 3 matrices, you should wind up with a 2 by 2 matrix. The first column is 0, minus 3. The second column is 6, 0. So rather than apply 3 different transformations to each vertex, let me just take the product of these 3 matrices and then apply this one single matrix to each of these vertices. And that's going to tell me that this vertex at 1, 1 gets mapped right here. And I don't need to necessarily worry about how it gets mapped intermediately in between. And after performing this sequence of transformations, right, what we'll get is I just uncovered this triangle down below in orange is what I would get if I took this blue matrix and applied this transformation, the product of these 3 transformations. We would get straight to this orange triangle, which is exactly the same as what we wound up with if we first went to red, then went to the black triangle, and then finally mapped over onto this green triangle below. And one thing that's really important to note here is the order, what direction we're multiplying these matrices. So each time I apply the next operation, just keep in mind you're multiplying on the left of the previous product. So we start with S, then we apply V. So I multiply S on the left by V. Then we apply R, so I take V times S and I multiply that on the left by R. So we get RV times S. So let's summarize this on the next slide. Okay, so in summary, if I'm taking the composite of, for example, 3 linear transformations in the following order, we're first going to apply transformation given by matrix A, then apply a transformation which is multiplication by B, then transformation given by multiplication by matrix C. That's equivalent to just applying the matrix transformation given by the product of C times B times A, where the very first transformation is on the furthest on the right, and the very last transformation that we apply is all the way on the left. And so here I've indicated what we would do for 3 composition of 3 transformations. If we wanted to compose 4, 5, 6, 7, 8 transformations, it's the same idea. Just be sure the very first transformation is the matrix on the furthest to the right, and then you're adding each matrix to the left, and then the very last transformation should be the matrix that's furthest on the left in that product.